Welcome you all for the third session of air standard cycles. In this session, we are going to discuss about the problems on Otto cycle. Let us discuss one problem. A 4-cylinder, 4-stroke. கட் பண்ணிக்கலாம் போட்டுங்க. A 4-cylinder, 4-stroke SI engine working on Otto cycle has 250 mm bore and 375 mm stroke. The clearance volume is 0.01052 meter cube. The initial pressure and temperature are 1 bar and 47 degrees Celsius. The maximum pressure in the cycle is limited to 25 bar. Determine thermal efficiency of the cycle and mean effective pressure. So this is the problem that we are going to discuss now, and let us write the given data first. Given data, the number of cylinders 4. The number of cylinder is 4K, and the diameter of the cylinder, that is bore is 250 mm, and stroke is 375 mm. The clearance volume is VC, that is equal to V2, is 0.01052 meter cube, and pressure at the inlet is 1 bar, at the initial stage is 1 bar, and temperature, initial temperature is 47 plus 273, 320 Kelvin. The maximum pressure in the cycle is Pmax, that is equal to P3 is equal to 25 bar. And now we have to find case 1 thermal efficiency of the cycle, and case 2 is the mean effective pressure. So we have to start with some assumptions. The assumptions are: air is used as the working medium, hence gamma is equal to 1.4, Cp is equal to 1.005 kilojoule by kilogram Kelvin, and Cv is equal to 0.718 kilojoule by kilogram Kelvin, and R is equal to 0.287 kilojoule by kilogram Kelvin. Now we have to solve this problem. Solution. Before starting a solution, let us draw the PV diagram. So the PV diagram, if you draw the PV diagram, this is the PV diagram. The process 1 to 2 is a compression process, and 2 to 3 is a constant volume heat addition, and 3 to 4 is the isentropic expansion, and 4 to 1 is the constant volume heat rejection. So here the process is PV power gamma is equal to constant. Here the process is PV power gamma is equal to constant, and here the heat is at process 2 to 3, the heat is added, heat is supplied, and in process 4 to 1, heat is rejected. So this is the PV diagram. Process 1 to 2 is a compression process, isentropic compression. 2 to 3 is the constant volume heat addition. 3 to 4 isentropic expansion. 4 to 1 is the constant volume heat rejection process. And here this is the clearance volume Vc, and this is the swept volume Vs. Okay, and this is also equivalent to V2, and this is equivalent to V1. So now we have to solve this problem. To solve this problem, let us start from here. The case 1. Case 1 is the thermal efficiency of the cycle. Thermal efficiency of the cycle. And in this one, we have to find out thermal efficiency, for which we need to find first compression ratio. So let us start with the compression ratio. To find the compression ratio, we need swept volume. It is equal to pi by 4 T square L into K. So pi by 4, D is actually a bore, which is 0.25 the whole square, and L is a stroke, which is 0.375, and number of cylinder is 4. So you will get pi divided by 4 into 0.25 square into 0.375 into 4. So you have 0.07363 meter cube. This is Vs. Now we have to find out V1. V1 is equal to Vc plus Vs. V1 is equal to Vc plus Vs. We know Vc, which is equivalent to V2, therefore 0.01052 plus 0.07363 is equal to, so 0.01052 plus 0.07363, you will get 0.08415 meter cube. This is V1. Now I have to find out what is the compression ratio R, that is equal to V1 by V2. The compression ratio is V1 by V2. I know V1, volume at initial stage, entry 0.08415, and this is the volume after compression So I'll get the ratio like this: 0.08415 divided by 0.01052. The answer is approximately 8. So compression ratio is now 8. Once we get compression ratio, then we have to find out the thermal efficiency. The thermal efficiency of an Otto cycle is equal to 1 minus 1 by R power gamma minus 1. So we know the compression ratio is 8, 1 by 8 power 1.4 minus 1. So we get now the answer as, so 8 power 0.4, so it's 56.5647, that is equal to 56.47% is the thermal efficiency. Okay, so this is the one answer we get. Now we have to find out the case 2, mean effective pressure. For finding mean effective pressure, let us start with finding out the temperature after compression. So after compression, the temperature is T2. I have to find T2. T2 is equal to T1 into R power gamma minus 1. So that T1 is the value, T1 is 320 Kelvin. So 328 power 1.4 minus 1 is equal to 320 into 8 power 0.4 is 735.17 Kelvin. Then we have to find out P2. P2 is equal to P1 into R power gamma. So what is P1? It is 1 bar. So 1 into 8 power 1.4, which is equivalent to 18.38 bar. Now we know P3, maximum pressure in the cycle. Then we have to find out P3. T3 is equal to P3 by P2 into T2. This is the formula, because the process 2 to 3 is a constant volume process. For a constant volume process, we get the PVT relationship as T3 by T2 is equal to P3 by P2. From this, we can find T3. So we know T3, we have to find T3. Then P3 we know, which is 25 bar, and P2 we know it is 18.38 bar, and T2 we know it is 735.17. So we get now 25 by 18.38 into 735.17 is 999.96 Kelvin. So then we have to find out mass flow rate, mass of air handled per cycle. So M is equal to P1 V1 by R T1. P1 we know it as 1 bar. I can write in terms of 100 kilopascal into the initial volume, which we have found out here as 0.08415 meter cube. So that I am substituting here, 0.08415 divided by R, the gas constant, which is 0.287 kilojoule per kilogram Kelvin. Since I am substituting P1 in terms of kilopascal, I am substituting R in terms of kilojoule per kilogram Kelvin, into the temperature T1 is 320. So now if you calculate these values, 100 into 0.08415 divided by 0.287 and divided by 320, you get 0.0916 kilogram of air. Okay, 0.0916 kilogram of air we get for mass. Now what is the heat supplied? So heat supplied, Q heat supplied is equal to M into CV into T3 minus T2. right? So mass we have found out as 0.0916, CV it is 0.718 kilojoule per kilogram Kelvin, and T3 we found as 999.96, and T2 it is 735.17. So we get the heat supplied as 0.0916 into 0.718 into the difference between 999.96 minus 735.17. So I get now 17.42, 17 point, we can write even 415 kilojoule. So this is the amount of heat supplied. Now I want what is the work done. Why I am finding work done? Because mean effective pressure is nothing but the work done by swept volume. So I am finding the work done. So work done is equal to heat supplied into efficiency of thermal cycle. So now I substitute heat supplied, which is 17.415 into the thermal efficiency. I get as 0.5647. So this value I am substituting here, 0.5647. So I get now 17.415 into 0.5647 is equal to 9.83, 9.834 kilojoule. And then I have to find out the mean effective pressure. The mean effective pressure now is equal to mean effective pressure is equal to work done by swept volume. So work done is equal to, we have 9.834 kilojoule per kilogram, kilojoule, 9.834 kilojoule. So 9.834 kilojoule divided by the swept volume. We have found out here it is 0.07363 meter cube. So 0.07363, I get now 9.834 divided by 0.07363 is 133.56 kilopascal, or I can write 1.33, I can write 1.34 bar. Okay, so this is the mean effective pressure. This is the mean effective pressure. Right, 1.34 bar. So we have now found out that the thermal efficiency as 56.47 percentage and mean effective pressure as 1.34 bar. If you see here, the temperature at the end of the compression is more than at the inlet because it is isentropic compression process, and the temperature at the end of heat addition T3 is more than T2 because during the process 2 to 3 the heat is added at constant volume. So naturally the temperature at third state will be more than the second state. We will discuss another problem in Otto cycle. A SI engine operating on Otto cycle has total volume 0.45 meter cube, pressure 1 bar, and temperature 27 degrees Celsius at the beginning of compression stroke. the pressure at the end of compression stroke is 11 bar and 210 kilojoule of heat is added at constant volume. Determine pressure, temperature and volume at all salient points percentage clearance volume and power developed by the engine if number of working cycles per minute is 250. Now we will write the given data. The given data are P1 is equal to 1 bar, T1 is equal to 37 plus 273, 300 Kelvin, and V1 is equal to 0.45 meter cube, P2 is equal to 11 bar, heat supplied is equal to 210 kilojoule, and number of working cycles is equal to 250 cycles per minute. Now we have to find, in case 1 we know P1, T1, V1, then we have to, on P2. So we have to find T2 and V2, comma, P3, T3, V3, P4, T4 and V4 in case 1. Case 2, we have to find out percentage clearance volume, and case 3, power developed. So we have to start with some assumptions. Assumption: air is the working medium, hence gamma is equal to 1.4, Cp is equal to 1.005 kilojoule by kilogram Kelvin, and Cv 0.718 kilojoule per kilogram Kelvin, and R is equal to 287.287 kilojoule per kilogram Kelvin. So now we have to give a solution for the problem. Let us draw a PV diagram for this Otto cycle. So this is the PV diagram. In a PV diagram, the process 1 to 2 for Otto cycle is isentropic compression. So this process is isentropic compression. Then 2 to 3 process is a constant volume heat addition. Then 3 to 4 is an isentropic expansion process. So PV power gamma is equal to constant, and four to one is constant volume heat rejection. Constant volume heat rejection process. So now we will mark out the clearance volume and swept volume here. So this is clearance volume and this one is a swept volume, and this V2 is equal to V3 and V4 is equal to V1. This point and this point. All right. So now we have to solve this problem. To start with, the case 1 is we have to find out T2, V2, P3, T3, V3, P4, T4 and V4. So we have to find out all these things. Now V1 is the known value and P2 and P1 are also known value. So I need to find what is V2. So V2 by V1 is equal to P1 by P2 power 1 by gamma. I need V2, therefore V2 is equal to V1 into P1 by P2 power 1 by gamma. So we know V1, so substitute that, which is 0.45, and P1 is a 1 bar and P2 is 11 bar, power 1 divided by 1.4. So we get V2 is equal to 0.45 into 1 divided by 11 power 1 divided by 1.4. So I get 0.08116 meter cube. So this is V2. Now I have to find the R value, compression ratio. So R is equal to V1 by V2. So V1 we know it is 0.45 meter cube. So 0.45 divided by 0.08116 is equal to 0.45 divided by 0.08116 is 5.55. So R is equal to 5.55. So this is the value of compression ratio. Now from that I have to find out T2. So V2 we have found out, then T2 is equal to T1 into R power gamma minus 1. T1 is the known value given in the problem, 327 degrees Celsius, which means 300 Kelvin, and R is 5.55, power gamma 1.4 minus 1. So I get T2 is equal to 300 into 5.55 power 0.4. So 595.44 Kelvin. So this is T2. Now we have to find T3 because the heat added at constant volume is given. So we can write heat supplied is equal to mass into Cv into T3 minus T2. Here we know T2, we know Cv and we know heat supplied. Once we find mass handled, mass of air handled per cycle, we can get the T3. So how to find mass of air handled per cycle? M is equal to P1 V1 divided by RT1. The pressure at initial stage is 1 bar, that I am substituting in terms of kilopascal. So 100 kilopascal into V1 is 0.45 meter cube and R is 0.287 kilojoule per kilogram Kelvin. As I substitute P1 in terms of kilopascal, here we have to substitute in terms of kilojoule per kilogram Kelvin, and T1 is a 300 Kelvin. So I will get the mass is equal to, mass of air handled is equal to 100 into 0.45 divided by 0.287 divided by 300 is 0.5226 kilogram of air per cycle. All right. So 0.5226 kilogram per cycle. And we have to now find out T3, substituting the mass flow rate in a heat supplied equation. You get 210 kilojoule is equal to 0.5226 kilogram per cycle into Cv value is 0.718. We do not know T3, that we have to find out, and T2 is 595.44. So now we get the T3 value as 210 divided by 0.5226 divided by 0.718 plus 595.44. The value is 1155.1 Kelvin. So now we know T3, then we have to find out P3 as well as V3. To find P3, the process 2 to 3 is a constant volume process. So I can write the PVT relationship as T3 is equal to Tt by T2 into P2. The T3 is 1155.1 and T2 is 595.44 and P2 is 11 bar. Therefore, we get P3 is equal to 1155.1 into 11 divided by 595.44. We get 21.34 bar. That is P3. Now we have to find out P4 and T4. So, and not only that, the V3 is equal to V2, that also we have to write here. So V3, that is equal to V2, that is equal to, we know V2 as 0.08116 meter cube. So we found out now V2, T2, P3, T3, V3, the remaining are P4, T4 and V4. So how to find the P4? P4 is equal to P3 divided by R power gamma. So what is P3? P3 is 21.34 and the R value is 5.55 power 1.4. Therefore, P4 is equal to 21.34 divided by 5.55 power 1.4, which is 1.937 bar. 1.937 bar. Then we have to find out T4 and V4. T4 is equal to T3 by R power gamma minus 1. T3 we have found out as 1155.1. So 1155.1 divided by 5.55 power 1.4 minus 1. So we get T4 is equal to, so 1155.1 divided by 5.55 power 0.4, which is 581.97 Kelvin. Then the V4 we have to find out. Since process 4 to 1 is a constant volume process, V4 is equal to V1 is equal to 0.45 meter cube. So we found P4, V4, T4. So all the unknown properties at all salient points we have found out. Now we have to find out what is the percentage clearance volume. The second one is a percentage clearance volume for which we have to find out Vs first. The Vs is equal to V1 minus V2, you can see here. So this is Vs. So to find this Vs, we have to find what is V1, then we subtract this V2. So V1 minus V2 is the swept volume. We know V1 is given as 0.45 meter cube. So 0.45 minus V2 we already found out here 0.08116. So substitute that 0.08116. So we get the swept volume as 0.45 minus 0.08116 is equal to 0.36884 meter cube. And then we have to find out what is clearance volume. Clearance volume, that is equal to V2, that is equal to 0.08116 meter cube. So we have to find what is the percentage clearance volume. Percentage clearance volume is equal to Vc by Vs into 100. So what is Vc? Vc is equal to V2, that is 0.08116 divided by the swept volume 0.36884 into so 0.08116 divided by 0.36884 into 100. So we get 22 percentage clearance volume is equal to 22 percentage. So now we have to find out what is the power developed by the engine. What is the power developed by the engine? Case 3. Power developed by the engine. In this case, we have to find out what is the efficiency of the engine. That is first. Efficiency of a Otto cycle is equal to 1 minus 1 by R power gamma minus 1. That is equal to 1 minus 1 by 5.55 power 1.4 minus 1. So from this I can find what is efficiency of Otto cycle. So the efficiency is 0.496162, that is equal to 49.62%. So this is the efficiency of the Otto cycle. And now we have to find out what is the work developed. We have to find out what is the work developed. So work produced or developed per cycle is equal to efficiency of Otto cycle into heat supplied. So we know efficiency of Otto cycle as 0.4962. So 0.4962 into the heat supplied is 210 kilojoule, that you put, you will get the work done as 0.4962 into 250. Actually this okay, 210, that's correct. 210, 0.4962 to 210, we get 104.2 kilojoule. Now, what is the power developed? Power developed by the engine is equal to work developed per cycle into number of working cycles per second. So 104.2 into 250 by 60 is equal to 104.2 into 250 by 60 is equal to 434.17 kilowatt. So this is the power developed. So we have found out all the properties as salient points and percentage clearance volume and work developed. If you look at here, the temperature at T2 is more than T1. Since it is a compression process, isentropic compression, it will be more than that. From process 2 to 3, there is a heat supply taking place to 10 kilojoule. Therefore, the heat is released as the temperature is more than T3, more than T2. T3 is more than T2. And 3 to 4 is an expansion process. The temperature will get reduced. So 4 to 1 is a heat rejection process. So the heat is released during the 4 to 1, rejected to the atmosphere. And the total power developed in this SI engine is 434.17 kilowatt.